Have you ever watched a mountain come apart in slow motion, not over thousands of years through ordinary erosion, and not during a violent earthquake, but while scientists stood nearby measuring its movement centimeter by centimeter as enormous cracks widened across the landscape? What happens when an entire section of a ridge begins sliding downhill week after week, yet refuses to collapse in the catastrophic way geology textbooks often predict? And how can millions of tons of rock remain in motion without suddenly breaking apart? Can modern monitoring systems truly forecast the behavior of a moving mountain, or are there limits to what even the most advanced instruments can reveal about the hidden forces operating deep beneath the surface? These questions came sharply into focus at Rattlesnake Ridge in Washington state, where one of the most closely studied landslides in North America transformed an ordinary mountain slope into a natural laboratory for understanding the mechanics of slope failure. To many observers, the widening fissures looked like evidence that the mountain itself was splitting in two, but geologists quickly recognized that something more complex was unfolding. The dramatic cracks visible at the surface were not the cause of the movement, but rather the visible symptoms of a much larger geological process occurring deep inside the ridge. What emerged from years of monitoring was a remarkable story of gravity, rock mechanics, groundwater, and ancient volcanic layers interacting in ways that challenged conventional expectations about how large landslides behave. To understand why Rattlesnake Ridge began moving, it is necessary to look millions of years into the past when enormous volcanic eruptions created the rocks that now make up much of central Washington. The region lies within the Yakima Fold Belt, an area shaped by tectonic compression that bent and folded thick sequences of basalt produced by the immense eruptions of the Columbia River basalt group. Unlike explosive volcanoes that build steep cones through violent eruptions, these ancient events released huge volumes of fluid lava that spread across vast distances, creating stacked layers of basalt hundreds to thousands of feet thick, equivalent to several hundred meters in many places. Each lava flow cooled differently, producing dense interiors surrounded by more fractured and sometimes weathered upper and lower zones. Between successive flows, periods of volcanic inactivity allowed sediments to accumulate, weathering to occur, and weaker materials to develop. Over millions of years, these contrasting layers became buried beneath additional volcanic deposits and tectonic deformation. The result was a mountain composed not of a single uniform rock mass, but of multiple layers possessing very different mechanical properties. This geological architecture would eventually become the key factor controlling the future instability of the ridge. One of the most important principles in landslide science is that slopes almost never fail through their strongest materials. Instead, gravity exploits existing weaknesses, and when enough stress accumulates above a weak layer, failure begins where resistance is lowest rather than where rock is strongest. At Rattlesnake Ridge, investigations revealed that a large mass of basalt was sliding along weaker sedimentary material hidden beneath portions of the mountain. This meant that the ridge was not disintegrating throughout its entire structure, but was instead behaving like an enormous block moving across a comparatively weak surface. The distinction is crucial because it explains why the landslide developed such dramatic surface fractures while still maintaining much of its internal coherence. Rather than collapsing into a chaotic debris flow, the moving mass largely retained its shape as it shifted downhill. Geologists classify this type of behavior as a translational landslide, meaning that movement occurs along a relatively planar surface rather than a curved one. The process resembles pushing a giant slab across a surface rather than rotating it forward, and this geometry controlled nearly every aspect of the deformation observed at the site. As the landslide progressed, the upper portions of the moving block experienced stretching forces that exceeded the tensile strength of the rock. When rock is pulled apart faster than it can accommodate the stress through elastic deformation, fractures develop. These fractures formed the spectacular tension cracks that attracted international attention and created the impression that the mountain was being torn apart. However, the cracks themselves were merely indicators of deeper processes already underway. The true movement occurred along the hidden failure surface where millions of tons of rock slowly slid over weaker material beneath the ridge. Because different sections of the moving block traveled at slightly different speeds, stress accumulated unevenly throughout the slope. Some areas stretched apart while others compressed, generating a complex network of fractures that reflected the distribution of forces inside the landslide. Every widening fissure therefore provided clues about how stress was being redistributed through the mountain. The visible cracking was not evidence of separate pieces moving independently, but rather signs that an enormous coherent mass was gradually adjusting to gravitational forces. When the instability became widely recognized during 2017, scientists responded by deploying one of the most comprehensive landslide monitoring programs ever established in the United States. High-precision global positioning system stations tracked movement with extraordinary accuracy. Ground-based radar systems measured displacement across large portions of the slope. Seismic instruments detected internal cracking and rockfall activity. Drones repeatedly mapped surface changes, and engineers constructed detailed three-dimensional models that were updated as new data became available. The resulting observations revealed a pattern that surprised many specialists. Portions of the landslide moved approximately 1 1/2 to 1 7/10 feet per week, equivalent to roughly 45 to 52 centimeters weekly, while daily movement rates sometimes reached 6 to 7 centimeters. These rates are extremely rapid for a landslide, involving millions of cubic yards of material, and would correspond to annual movement of roughly 25 to 30 meters if maintained continuously. At the same time, the main tension crack widened by approximately 1 foot, or 30 centimeters per week during the most active periods. Such movement was fast enough to be visible over short time intervals, yet slow enough to permit continuous observation and analysis. Perhaps the most scientifically significant discovery was that the landslide did not accelerate in the way many geologists expected. Catastrophic slope failures often display a characteristic pattern in which displacement rates increase exponentially as collapse approaches, creating a feedback loop where movement reduces resistance, which in turn promotes even faster movement. At Rattlesnake Ridge, however, displacement remained comparatively steady despite the dramatic appearance of the fissures. This suggested that the landslide occupied a delicate balance between driving forces and resisting forces. Gravity constantly pulled the mass downslope, but friction along the failure surface continued to provide substantial resistance. As movement occurred, stress redistributed throughout the block, creating new patterns of loading and unloading. Some areas weakened while others effectively strengthened due to changes in contact conditions along the sliding surface. Instead of progressing toward an inevitable runaway collapse, the landslide repeatedly found temporary states of equilibrium that allowed movement to continue without catastrophic failure. This behavior challenged assumptions about how large translational landslides evolve and demonstrated that visible cracking alone is not necessarily evidence that collapse is imminent. The concept of shear strength is central to understanding why the slope moved at all. Every geological material possesses a limit beyond which it can no longer resist deformation, and when the stresses acting on a slope exceed the available shear strength, movement begins. Shear strength depends on many factors including mineral composition, fracture density, grain size, weathering history, and the presence of water. Among these influences, groundwater often plays the most important role because it directly affects effective stress within rock and soil. Water occupies tiny pore spaces between particles and fractures, and when pore pressure increases, it reduces the forces holding materials together. As effective stress decreases, shear strength declines, making it easier for gravity to overcome resistance. Although Rattlesnake Ridge was not simply triggered by rainfall, groundwater likely contributed to the long-term weakening of the failure surface. Water moving through fractures and weak sedimentary horizons probably reduced strength over extended periods, gradually preparing the slope for eventual instability. In this way, groundwater acted not as a sudden trigger, but as a persistent geological agent that slowly altered the mechanical behavior of the mountain. Another critical concept is progressive failure, a process in which instability develops gradually rather than all at once. Mountains do not usually collapse because a single crack suddenly appears. Instead, small fractures form in localized areas, stress shifts into neighboring regions, additional fractures develop, and isolated damage zones slowly connect into larger networks. Over time, these networks merge into a continuous failure surface capable of supporting large-scale movement. By the time the dramatic fissures appeared at Rattlesnake Ridge, much of this hidden evolution had likely already taken place underground. The visible cracks represented the latest stage of a process that may have been developing for years, or even decades. This perspective is important because it highlights the difference between observing a landslide and understanding its origins. What people see at the surface is often only the final expression of a much longer geological history occurring beneath their feet. The apparent suddenness of many landslides therefore reflects limitations in human observation, rather than truly sudden geological change. The immense size of the unstable mass introduced additional complexity. Estimates suggested that the affected area covered roughly 20 acres and contained somewhere between 3 million and more than 5 million cubic yards of rock and soil. A moving body of this scale behaves differently from smaller landslides because its enormous mass creates substantial inertia. Large systems tend to respond more slowly to changes in stress conditions, and this can produce movement patterns that appear surprisingly stable despite ongoing deformation. Instead of fragmenting immediately, the landslide acted somewhat like a giant raft composed of fractured basalt, moving as a largely coherent block. Internal deformation certainly occurred, but much of the mass remained structurally connected throughout the active phase of movement. This coherence helped explain why catastrophic collapse became increasingly unlikely as monitoring data accumulated. Scientists recognized that the landslide was capable of significant displacement without necessarily transitioning into a rapid debris avalanche. The mountain was moving, but it was doing so according to a set of mechanical constraints that limited the speed and style of failure. The famous tension crack offered a remarkable opportunity to study fracture propagation in real time. As the main block moved downslope, extensional forces concentrated near the crown of the landslide. Once these forces exceeded the tensile strength of the rock, fractures opened and expanded. Yet the geological significance of the crack extended beyond its initial formation, because fractures alter the physical behavior of slopes in multiple ways. Newly opened pathways allow water to infiltrate deeper into the rock mass, accelerating weathering and changing groundwater flow patterns. During colder periods, freeze-thaw cycles can further enlarge fractures, as expanding ice exerts pressure on crack walls. Weathering processes attack fresh rock surfaces exposed by the fractures, weakening them over time. Consequently, the crack became both a consequence of movement and a factor influencing future deformation. This type of feedback is common in active landslides and demonstrates how geological systems evolve through interactions between mechanical failure and environmental processes. The widening fissure was therefore not simply a passive feature, but an active participant in the ongoing evolution of the slope. One reason Rattlesnake Ridge attracted such intense scientific interest was the exceptional quality of the monitoring data. Many major landslides occur suddenly and leave researchers attempting to reconstruct events after the fact. In contrast, this landslide unfolded gradually enough to allow direct observation of its development. Scientists were able to compare predictions with real-world behavior, test competing models, and refine their understanding of large translational failures. The extensive dataset revealed that no single measurement could fully explain the landslide. Global positioning system data showed displacement patterns, radar documented movement across broad areas, seismic sensors detected internal activity, and geological mapping revealed structural controls. Each method illuminated a different aspect of the problem, and only by combining them could researchers build a comprehensive picture of the processes at work. The resulting knowledge has implications far beyond Washington, because similar geological conditions exist in many volcanic and mountainous regions around the world. Understanding how strong rock masses slide over weak layers is essential for assessing landslide hazards in countless landscapes. The event also demonstrated the importance of geological structure in determining slope stability. Many people assume that steep slopes are inherently dangerous while gentler slopes are relatively safe. In reality, internal structure often matters more than slope angle alone. A moderately inclined hillside containing weak layers oriented in unfavorable directions can fail more easily than a steeper slope composed of strong, well-bonded rock. At Rattlesnake Ridge, the arrangement of basalt flows, sedimentary layers, and fractures controlled how stresses were transmitted through the mountain. Weak horizons provided pathways for movement, while structural discontinuities influenced the development of fractures. The landslide therefore reflected the internal architecture of the ridge just as much as its visible topography. Understanding this relationship between structure and stability remains one of the central challenges in engineering geology, because hidden subsurface conditions often determine whether a slope remains stable or eventually begins to move. As monitoring continued over subsequent years, displacement rates gradually declined. This slowdown became one of the most important observations of the entire event, because it suggested that the system was evolving toward a more stable mechanical state. Several factors may have contributed. Material accumulating near the base of the landslide created a natural buttress that increased resistance to further movement. Stress redistribution altered force balances throughout the slope. Some sections of the failure surface may have encountered rougher material capable of generating greater friction. Changes in groundwater conditions could also have influenced the availability of shear strength. Whatever the precise combination of mechanisms, the result was a measurable reduction in movement. Importantly, stabilization did not mean that the mountain returned to its original condition. The fractures remained, the failure surface persisted, and the geological damage was permanent. The ridge had simply transitioned into a new equilibrium, one defined by altered stress distributions and a different balance between driving and resisting forces. As of 2026, no catastrophic collapse has occurred, and the scientific interpretation of the landslide remains largely unchanged. The evidence continues to support the conclusion that Rattlesnake Ridge represents a large translational landslide driven by gravitational movement of basalt blocks over weaker underlying material rather than by tectonic faulting or earthquake-related rupture. This distinction matters because it places the event within a broader framework of slope evolution rather than crustal deformation. The ridge is not splitting apart because tectonic plates are pulling the ground in opposite directions. It is moving because gravity has found a weakness within the mountain's internal structure and is slowly exploiting that weakness over time. That explanation may seem less dramatic than images of a mountain tearing itself apart, but from a geological perspective, it is far more revealing. It exposes the hidden mechanics governing slope stability and provides a rare glimpse into processes that shape landscapes throughout the world. In the end, Rattlesnake Ridge serves as a powerful reminder that mountains are not permanent monuments frozen in time. They are dynamic systems continuously responding to gravity, groundwater, weathering, tectonic stress, and the mechanical properties of the rocks from which they are built. The landscape visible today represents only a temporary balance among these competing influences. At Rattlesnake Ridge, that balance shifted enough to set millions of cubic yards of rock in motion, creating one of the most thoroughly documented landslides in modern geological history. Scientists measured every stage of the process, mapped the fractures, monitored the displacement, and developed increasingly sophisticated models. Yet one reality remained unchanged throughout the event. Human beings could observe the movement, analyze its causes, and estimate its future behavior, but they could not stop it. The mountain followed the laws of physics and geology rather than human expectations, revealing with unusual clarity how ancient volcanic layers, buried weaknesses, friction, groundwater, and gravity continue to reshape the Earth's surface long after the forces that created the landscape have faded into geological history.